going to be analyzing the function -1 to the x for real x. If you only consider this function in a range of real numbers, then your domain is going to be limited to the rational numbers with odd denominator. But if you consider this over the complex numbers, then this function is more versatile. For example, you might think -1 to the 1 over 2 is I. This is how we define the square root of -1. But what about -3 to the -1 to the 3 over 14, or -1 to the golden ratio? Well, let's just look at some complex number fundamentals that will help us define this function fully. So every complex number can be written as a conjunction of a real part, here in yellow, and an imaginary part, here in blue. And we write this as the real part plus I times the imaginary part, and we get a complex number. If you're familiar with two-dimensional vector addition, you can think of this as just adding two unit vectors together, where one axis is a real axis and another axis is the imaginary axis. When you add these two together, it forms a right triangle, where the height is the imaginary part, the base is the real part, and there's this hypotenuse here. The length of the hypotenuse is what we call the modulus of our complex number z. And the angle from the right-hand side of the x-axis to the hypotenuse is called the argument of z. This we can use to prove something. So we've taken some complex number z, and we write it as a plus ib, and we factor out the modulus of z. But from the right triangle here, this is just the modulus of z times the cosine of the argument of z plus I times the sine of the argument of z. Therefore, every complex number can be written in the form of its modulus and you multiply it by a function of its argument. And just as a shorthand, we call this function cis, which is short for cosine I sine. Okay? So let's just take two arbitrary complex numbers, and one is s times cis alpha, and the other is t times cis beta. And when you multiply these two together, you get s times cis alpha times t times cis beta. If you expand that out, you get st times cos alpha plus sine alpha times cos beta plus I sine beta. Then if you multiply out this further, st times cos alpha times cos beta minus sine alpha times sine beta plus I sine plus I cos alpha times sine beta plus sine alpha times cos beta. But these are just the double angle formulas, the compound angle formulas of cos alpha plus beta and sine alpha plus beta. So this is st times cos alpha plus beta plus I sine alpha plus beta, which is st times cis alpha plus beta. As a result, that means that when you multiply two complex numbers together, you multiply their moduli, and you add their arguments. Let's go back to -1 to the x, because I seem to have gone off on a tangent here, but I promise that this is relevant. So there are two defining features of this function here that we want to maintain. So for any even number, -1 to any even number is equal to 1, and -1 to any odd integer is equal to -1. Furthermore, what I believe to be the defining property of exponential functions is when you multiply -1 to the x times -1 to the y, you get -1 to the x plus y. Okay. Well, this is pretty similar to what we saw over here, because when you multiplied cis alpha and cis beta, you got cis alpha plus beta. Let's just see how we can use this. So earlier we said that -1 to the 1 over 2 is I, but I'm going to show you a process that allows us to get to that point. So we need a complex number, -1 to the 1 over 2, such that -1 to the 1 over 2 times -1 to the 1 over 2 is equal to -1. Therefore, the modulus of -1 to the 1 over 2 is 1, and the argument of -1 to the 1 over 2 is 1 of pi over 2 and 3 pi over 2. So here we're just stuck in a pickle because we don't really know which one of these it is, but we're defining a function. So we'll just say that we define -1 to the 1 over 2 as I. And this just happens to be cis pi over 2. By the same line of reasoning, we need a complex number for -1 to the 1 over 3, such that -1 to the 1 over 3 cubed, that being multiplied by itself 3 times, is equal to -1. Well, -1 is a solution here. Indeed, -1 times -1 times -1 is equal to -1. But if we define -1 to the 1 over 2 as I, which is cis pi over 2, wouldn't it be more useful if we define -1 to the 1 over 3 as cis pi over 3? Indeed, if we look at a unit circle here, then cis pi over 3 is here, roughly. Then if you do another third turn, here's cis 2 pi over 3. And here is cis 3 pi over 3, which is cis pi, which is -1. So -1 to the 1 over 3, if you multiply -1 to the 1 over 3 times -1 to the 1 over 3, you get -1 to the 2 over 3, then -1 to the 3 over 3, which is -1. So that definition we gave earlier is consistent. And furthermore, I showed this on the unit circle earlier, but just wanted to write this down. -1 to the 2 over 3 equals -1 to the 1 over 3 times -1 to the 1 over 3, which we defined as cis pi over 3 times cis pi over 3, which is cis 2 pi over 3. So, without loss of generality, we can say that for any rational number written as m over n, we can define this as cis pi m over n. Now, what about for the irrational numbers? Because this line of reasoning doesn't hold for it. Well, let's just go back to our unit circle. So let's just say that we want to define -1 to the square root of 2. Well, the square root of 2 equals 1.41426 on and on, right? Well, if you cut off the decimal at some point here, let's just say you cut it off at 1, then you cut it off at 4, then you cut it off at 1, then 4, then 2, then 6, then each of these are defined rational numbers. So -1 to the 1 is over here. Then over here. Then -1 to the 1.4 is over here. -1 to the 1.41 is over here. 1.414, 1.4142, 1.4126 just keeps getting smaller and smaller, and it approaches it on this unit circle. Well, this is just we can say this rigorously as if we have a sequence of rational numbers such that it approaches an irrational number, then -1 to the irrational number, we define this as the limit of -1 to the sequence of rational numbers, which is just the limit of this of cis pi, the sequence of rational numbers. And since the cis function is continuous, this is cis pi times our irrational number. Therefore, for all real numbers, we can define -1 to the x as cis pi x. That's it. In the next video, I'm going to be talking about how we can use this identity to prove a fundamental, or not prove, but to demonstrate a fundamental theorem of, or a fundamental axiom of the complex numbers. That's it. Thanks for watching.